We have we have a large head and neck database from we treat. Actually, head and neck is probably our busiest clinic. We have over a thousand cases of over 1,000 patients who have been treated by the same physician. All of them curated. So we had the data and we had the uh, knowledge in a way, but we wanted to figure out how we can use that data to move the needle forward, so to speak. So again, my name is Kritim Latifi. I'm from Moffitt Cancer Center in Tampa. And my main day-to-day job actually is dealing with a lot of adaptive radiotherapy, whether it's with the MR Linac or with Ethos system from Varian, or even offline adaptive using the RayStation tools that we have. So just wanted to disclaimer, this is what I'm going to show is strictly research. Nothing like this is available in the clinic yet, but hopefully in the future. Radiation oncology is a team sport. Just like the picture here, a fight between, uh, Tampa Bay Lightning and Toronto Maple Leafs happens pretty much multiple times during the year. We kind of physicists and physicians, we also have similar, not physical fights, but things like that. So a list of all the people that I collaborate with, both from Moffitt and from RaySearch. So as I said, we have a large database of quality plans. Um, our clinic plays a lot of or puts a lot of attention to dose homogeneity. So both the minimum dose to the target and also the maximum dose are very strict requirements, um, which leads to really good clinical data. So in a way, we kind of are sitting on gold mine here with a lot of really good data. My colleague here, Vladimir Fagelman, he's not here, but a bunch of his slides made it to San Francisco. So, um, just to go over quickly, um, published data show that PEG2 placement is pretty high, but when you look in the Moffitt data, actually, we are about half of what's been published out there. So this is kind of like the idea of why we wanted to do something with this data on the machine learning side. Even though this data is not matched of what's been published in papers and what we have, but still, when you compare what's out there, we see that our results are actually showing that there's much more improvement of what we have been getting for our patients. So, which leads to plan automation. As you know, head and neck, and generally planning dosimetry is dependent on the user or the planner. So it's more like an art actually. The more experienced somebody is, the better plans they produce. So we wanted to kind of see how we can automate the process. Back in the Pinnacle days, there was Pinnacle auto planning. We tried it ourselves as well, but also others. Um, Target coverage and homogeneity was an issue. Similar with Eclipse, similar deal. Homogeneity is also a challenge for those plans. Um, some other rapid plan papers that shows they evaluated plans at 2% or D2% and D98%. This is not something that would pass in our clinic. It would not be acceptable. So looking at data from RTOG, the RTOG 1016, for example, allows for a hotspot up to 82 gray or 117%, which is unacceptable in our clinic. And this is just a quick what we kind of accept. So it's pretty stringent requirement, 105% hotspot with what used to be collapse cone. With Monte Carlo, with RayStation, we accept up to 108% hotspot. If you move to head and neck 002, the requirements are a little bit stricter, but still 15% hotspot is unacceptable. Some papers for RaySearch Autoplanning also accept produce plans up to 115%. So it's again, it's high. Um, I think this was a paper from the Duke team. Their plans, their auto plans showed about 122% hotspot for head and neck. Just to kind of go back to our clinical goals, you can see it's pretty stringent goals. Uh, Minimum dose is evaluated at 0.03 cc, not at 1%. Similar to max dose is at essentially a voxel level, so it's 3.03 cc and other organs. So, which led to our collaboration with RaySearch and Frederick's team on trying to generate deep learning tools to kind of mimic what we do in the clinic. I don't need to explain this. The speaker before me kind of went over this, which was kind of nice. So used neural network to predict the dose, and then from that to mimic what the prediction shows. 54 patients were used for this particular model, and then all those patients were treated with VMAT, 70 grade to the primary, 56 to elective region, and then we used an independent 10 cases to validate this model. One thing to just, I think I skipped over. This is the model is not optimized for speed yet. Less than 30 minutes, it produces a deliverable plan for head and neck. So this is one of those cases. If on the left is what was clinically delivered, and that's actually a collapse cone pinnacle plan. On the right is a fully automated deep learning plan. For the same patients, same requirements, it's pretty much very similar plans. And DVHs here shows that they are quite similar. You can actually see in some of the OARs, the deep learning model does actually better protecting the OARs than the manual plan. This was one of my students took the 10 cases and evaluated what we got from the manual planning versus deep learning. Both produced similar plans. About out of the 10 cases, 7 of the 10 cases would have been acceptable by a physician, so we would be able to deliver those. 3 out of the 10 cases would require some more work in order to achieve the results. The nice thing about this is that even if it's a plan that is not acceptable yet, you can actually use that as a warm start for optimization and to keep going. So it makes things a little bit better. Just to show you here, if you look at these, actually these are evaluated at 0.03 cc. So it's kind of similar results, but it still would not be acceptable to our physician. By the way, if you validated those at 1% and or 99%, all of those would be acceptable, but that's not what we do. So here's a case that the deep learning model does very well. You can actually, if you look at those, you may not be able to tell which one is which. The one on the left actually is the auto plan or deep learning plan. The one on the right is the clinical plan. And here are the results. The only cases where it doesn't do as well is the oral cavity, because the deep learning model puts a lot of weight on coverage. Just to kind of see the slides here of that particular plan. So sometimes the model doesn't always meet our goals. It does pretty well everywhere else, except that we have found that in the minimum dose coverage has a hard time of meeting those, especially in cases that have a large targets. So if the tumor is large, likely the deep learning model is not going to perform as well. So in that sense, if upfront we know that we have large targets, we do manual planning from the symmetries. If we have relatively smaller targets, we can use auto planning. So you can kind of see here where this particular case where it fails, it's on the PTV 56. The minimum dose is way too low from what we would accept clinically. Um, another one where the minimum dose is not met. And so just so you guys know, this is an actual case. I sped it up a little bit. I ran it. It took about 25 minutes to run. And it was just a random case that I picked out of plans that had already been done previously. So in 25 minutes for this running on the RaySearch server, which is really just generic server that we use for doing training, the model produced not only a clinically acceptable plan, but it actually was superior to the manual plan. Let me just. It met, excuse me, it met everything that there was except the submandibular gland. And the only reason why it did not meet that was basically it was practically overlapping with the target, so it did not meet it. And then at the end, I compared it to the clinically acceptable plan or the deliverable plan, and you can see for yourself here in just a few seconds. So this is the plan that you just saw running. Everything about the right submandibular gland has not been met. This is the plan that was delivered. So actually, this auto plan not only met all the constraints, but it actually beat it, and this was in about 25 minutes. So this is really promising. May not be ready, but it's really nice to see that even in our clinic that our requirements are quite stringent on the dosimetry, and pretty much 100% coverage with 108% max. It's pretty tough to meet. So, and yet the model that we have trained with RaySearch's help seems to be able to actually do that. I think that's all I have. Thank you.
Thank you, thank you, thank you, thank you. Uh, it's great to see these results. And when you say that it's promising, what should happen next to make it from promising into clinically working,
Yeah.
robustly clinically working?
So we need to test it in way more cases. So we have gone through. So I did not show it, but actually these results have gone through multiple iterations. So we started. It's been about, I think, couple years project going on. Initially, the first stages produced a model that was placing a lot of emphasis on OAR sparing, but as a result, producing really cold plans. So our clinic actually is almost the opposite. It puts a lot of weight on the coverage, and sometimes even if the OARs are getting maybe a little bit too much dose, it it may be acceptable as long as the target goes all being met. So we went back and we modified those requirements, and then at some point we reached basically a saturation point where we realized that the mimicking algorithm that RaySearch was using was kind of like basically it reached a plateau. So at one point, I don't know the details. Frederick probably knows, and you guys know better than me. But they changed, they updated that algorithm. So then we went on to the last version with a new build of our testing research model that we have, and this is the last results. So at this point, it looks, I say it's promising because it's not ready for clinic yet. So we are going to do more testing to make sure to figure out exactly when it works and when does it work. It doesn't work. So we know that for the smaller targets, it's consistently producing really beautiful plants. And then once the target gets above a certain size, it's where it struggles. So it would be nice to actually upfront be able to tell that for this particular case, I'm just going to let the model do the work. For this particular case, then you have to decide whether the symmetrists start from scratch and do their job, or let the model produce an okay plan and the dosimetrist takes over. So that's kind of where we are now. But what I want for the future in a way is use what Anna was talking about earlier, deep learning segmentation. We also have evaluated algorithms that make or create acceptable cone beam CTs to be used for clinic for dose calculation. So the goal is to have basically a fully automated workflow where you use DLS, you apply correction to the cone beam CT of the day, you auto plan, all that basically doing automated. So you could technically do adaptive planning fully automated for head and neck, which is pretty cool.
It is pretty cool. And for that to make a reality, these technologies are needed. Would you agree?
Oh yes, I mean it's a version of this technology already exists on, if you're looking at the, let's say, MR Linac space. Like I'm lucky to be in a clinic that we have different tools, right? So MR Linac, we have online adaptive technology where you can do, adapt plans on the spot. Then you have, if you're looking at the variant solution, Ethos, similarly. But then it's not necessarily a competitive thing. It's more of like complementary solutions where if you have an MR Linac, but maybe your patient is not particularly a good solution for that, or Ethos, for head and neck cases, you may not need to adapt daily. So you may need to adapt maybe once a week or so. And this is exactly what's needed. So the tools are there. We just need to make them a little bit easier to use and more automated. So it doesn't require a lot of manpower. Like at Moffitt, we have a large clinic. We have 20 plus physicists. So we do have the people who can do this stuff, manually. But in a smaller clinic where the physicists are spending most of their time in clinical work, may not have the time to do this. So you need an automated solution.
Yes, agree. And as a software company, we are aligned to say that all the tools that exist, they should be supported. And by that, to have a software that would support everything would be the most
Definitely.
automated or fastest way.
Definitely.
But thank you, Kritim, for your presentation.
Thank you.
It was great to hear it. Give it
Thank
a
you.
applause.